Hi, welcome to Statistics Online. I'm Naomi Lowe, and today we will be giving Lecture 3, Part 1. So in Lecture 3, I'm going to give you a tool that you may be able to use. Last time we were together, we talked about how to calculate the mean and standard deviation and variance by hand, and hopefully you got a lot of practice, had fun doing all those even though they're a little tedious, learned exactly what you're doing when you calculate the mean, the median, the mode, standard deviation, and variance. And since you now know exactly what it means when you calculate those, I'm going to recap and give you a tool using Microsoft Excel where you can calculate them a little quicker. After that, we will move on to z-scores. I'm going to show you how to calculate a z-score from a raw score, how to take a raw score and convert it back to a z-score or get the raw score from the z-score. And then we'll talk about the normal curve in this Part 1 lecture. I'll introduce you to the normal curve, and then Part 2 of Lecture 3 will continue with the normal curve. We'll talk about samples and populations and talk a little bit about probability. Okay, so let's get started and move to Excel. Most computers have Excel on them. The campus computers all have Microsoft Excel, so if you have it, go ahead and open it up and you can work along with me. If you look in Excel, we have cells that you can type things into. For example, I can type in score, and it's just a label. I'm typing this in so I remember what I put in here. And well, let's make up some scores. We'll pretend these are IQ scores. 100, 104, 92. Now typically you wouldn't make these up. You would want to use real scores. 90. So we put 4 scores in there, but you can continue to add more scores to this sheet. And I'm going to show you how to quickly calculate the mean. In Excel, if you type in equals, it automatically assumes that you are going to use a formula in this cell. So you go ahead and type in equals to this cell, and then you can either click up here for a function that you last used, like the sum, or you can click this insert function button, the FX button. And when you do that, a box pops up and it gives you options. Typically it'll say most recently used, but for this class you will want to go to statistical tools. And you can see here you have several statistical tools. Here we want the mean, they call it the average. So you click on average, click OK, and now it gives you an option to choose which numbers you want the average of. And if you just minimize this by clicking this little box here, you can choose the scores. I'm going to highlight these scores, click Shift, highlight all of them, hit Enter, and it brings you back here. You could also type that in, cell A2 to A5. You can see this is cell A2 to A5. It's going to take the mean or the average of those. Click OK. And it's now calculated the mean. So instead of having to add up all the scores and divide by 4, you've calculated the mean. Okay. I'm going to show you how to use Excel to calculate standard deviation in addition to the mean very quickly. I will type in here SD. That's just my label to remind me that I'm calculating the standard deviation. Once again, if you want a formula, you type in equals. It changes it to formula mode. Click function. And I'm going to scroll down to S for standard deviation. Let's scroll down to, let's see. And here you see standard deviation. If you click on standard deviation, it tells you in Excel what it's doing. Here it says estimate standard deviation based on a sample. Based on a sample. You remember if we're calculating standard deviation with a sample, you're dividing by n-1. If you're calculating standard deviation with a population, you're just dividing by n. So the formulas are different. So you want to read the bottom of the screen and be careful that you choose the appropriate one. Since this is such a small sample, we're obviously, and this isn't my entire population, we'll click standard deviation for a sample. If you wanted to do standard deviation of a population, click down here and you can read at the bottom, it says based on an entire population. Here the formula is dividing by n instead of n-1. And so I click OK on standard deviation. It again gives me an option to choose what I want the standard deviation of. We'll minimize this, highlight these numbers, enter, brings us back here. We click OK. OK. And it's now calculated your standard deviation, 6.60. So this is a quick tool. I bet you're going, oh, I spent all last week calculating these by hand. You do need to know how to calculate these scores by hand. On the midterm and final, you will not be allowed to use Excel. You will not be able to use statistics programs, so you need to understand how to do it by hand. But when you're working through the rest of your homework and you already know how to do it by hand and you have to calculate the mean and standard deviation to plug it into other formulas, feel free to use Excel. It's a great tool for you. All right, let's move on to the rest of today's lecture. I'll go ahead and we are going to now talk about z-scores, and then I'll introduce you to the normal curve, and that will be all. All right. So a z-score is a score that gives you information about one particular raw score. When I say raw score, it's the original score that someone gets. For example, say someone got a score of 116 on an IQ test. Fred gets an IQ score of 116. Okay? That's great, but it doesn't tell us a whole lot about how he scored compared to all other people. So if I give you some information about whether Fred scored above average, below average, and how many standard deviations above and below average, it lets you know a little bit about Fred's score relative to other people's scores. So a z-score is just the number of standard deviations that a raw score is above or below the mean. It's how far a score is in terms of standard deviations, how many standard deviations the score is away from the mean. Okay, so Fred's IQ is 116. If I told you that the mean for this particular IQ test is 100, now you know that Fred's score is above the mean. So that tells you a little bit. But how far above the mean? Okay. What if the standard deviation is 100? That means he's barely above the mean at all. What if the standard deviation is 1? That means he's way above the mean. So it's important to know how many standard deviations above or below the mean he is, which is exactly what a z-score tells us. If I told you that this particular test had a standard deviation of 16, then you would know he's exactly 1 standard deviation above the mean. And his z-score would be 1, because the z-score tells you how many standard deviations above or below the mean the raw score is. So his raw score is 116, the z-score is 1. If he had scored 1 standard deviation below the mean, his z-score would be -1. So a positive z-score means you're above the mean, a negative z-score means you're below the mean. Now calculating a z-score is pretty simple. When you're calculating a z-score, all you need to do is take your score and subtract the mean from it. So if your score is larger than the mean, you end up with a positive number. If your score is smaller than the mean, you end up with a negative number. Telling you whether your score, your z-score, is positive or negative lets you know whether your score is above or below the mean. But we not only want to know whether your score is above or below the mean, we want to know how many standard deviations above or below the mean your score is. So then you divide by standard deviation. This formula can also be written as score minus the mean divided by standard deviation. So these are just 2 different ways to write this formula. As you should know by now, those are both interchangeable terms for mean and standard deviation. Now let's practice. If Frank took an IQ test, but he took this test in Japan, and the test is scored differently. Okay? The mean wasn't 100, the standard deviation wasn't 16. The test is scored differently. We want to compare his test to the last score that we looked at. This means nothing to us that his score was 50, because we don't know what the average score in this IQ test in Japan is or the standard deviation. But once I give you that information, I tell you that the mean equals 25 on this score. You go, wow, he's above the mean. And the standard deviation is 5. You can now calculate his z-score. So let's do it. Go ahead and do it with me. Let's take his score, 50 is the score, subtract the mean, 25, and divide by the standard deviation, 5. So 50 minus 25 is 25, divided by 5, and you get 5. And it's a positive 5. That's important to note. So this means that Frank's z-score on this IQ test is positive 5. That means Frank scored 5 standard deviations above the mean on this IQ score. So that's comparably high. It's very, very, very high. Frank did very well. If you were comparing this to the last score that we looked at of 116, there was only 1 standard deviation above the mean. This is a much better score. So essentially, z-scores standardize tests so that you can look at just the z-score and know how well they did on a test or how poorly they did on a test, even if the tests are all different, if they all have different point systems. Sometimes z-scores are called standard scores, standardized scores, because of this, because the standardized scores give you a standard way, a standard measure, a number, where you understand where that individual score falls according to the range, the mean, and the standard deviation of these scores, no matter what type of scoring system is used. All right, so let's do a little practice. So here, I want you to go ahead and try to calculate the z-scores for these tests. These are emotional intelligence tests, which a lot of times in the work field, they use EQ instead of IQ because they find someone can be really intelligent but not have an emotional intelligence where they're able to get along with other people, relay the information that they can to other people. So many times they give an EQ test instead of an IQ test. So here we have 2 different tests, test A and B. Test A was given at one point, and then they created a new version of the test, test B, that was scored differently. And I have the information for test A and test B down here, so you know the mean and the standard deviation of each of these tests. But this company is trying to decide who to hire, and they have 3 candidates who have taken these tests, 2 different types of tests, and they're not quite sure how to compare the 2 different scores with each other, so they decide to calculate z-scores. So I want you to go ahead and calculate z-scores. For the first 2, you will want to use test A information, and for the last one, you'll want to use test B information. So go ahead, calculate the z-scores, press pause on the video, and then come back. I'll give you the answers, and we'll see if you are on the right track. So each score minus that test's mean divided by the standard deviation, and that should give you the z-score. All right, I'll be back in a sec. All right, hopefully you calculated these scores on your own. If you did, these should be the scores that you got for your z-scores. If you didn't, I suggest you rewind, you look at z-scores again, you try it again, get the correct answers. Once you get the correct answers, we can answer this question. Who would you choose to hire? Okay, if you could only hire 2 candidates, who would you choose? Mary obviously scored very high, 2 standard deviations above the mean. Elizabeth scored 1 standard deviation below the mean, but Joe unfortunately scored 2 standard deviations below the mean. Poor Joe. So you probably go with the first 2 candidates. And you have a very good way of comparing these candidates, even though they took different tests. Okay. So now you can see how z-scores can be really useful. All right. Now, what if we had another candidate that came in, and this new candidate had a z-score of +3. That means that her score was 3 standard deviations above the mean. So this is not so good for the last candidate who was 1 standard deviation below the mean. She has a z-score of +3. You know that she's scoring 3 standard deviations. She's higher than anyone else. She's going to be the top candidate for this position. Now suppose she comes out and someone goes, wow, you had a z-score of +3. What was your test score? What did you get on your EQ, or emotional quotient, your emotional intelligence test? She might go, I don't know, they didn't show me my score. But if she knows the mean and standard deviation of this test, what this test usually has in a mean and standard deviation, the standard test, then she can calculate from her z-score what her actual raw score was. So suppose that she took test B. She took test B and she knows her z-score is +3. How can she calculate her raw score from the z-score? You just work backwards. So if you remember, z-score equals the raw score minus the mean divided by standard deviation. Okay? So right now we have her z-score. We know her z-score is 3. And we're asking the question, what was her raw score? But we know it's whatever it was minus the mean divided by standard deviation. We have the mean and standard deviation, so we can just plug those in. and we go 3 equals x minus 45 divided by 2.5. So now we just move things around and solve for x. So if we multiply by 2.5 on both sides, and then we add 45 to cancel that out, and add 45 to cancel that out. So go ahead with your calculator, and you want to 3 times 2.5 equals 7.5 plus 45 equals 52.5. So her score on this test was 52.5. Now let's look at the formula for calculating raw scores from a z-score. If you have a z-score and you have to work backwards to calculate a raw score, we know this is the formula. I just put the numbers in. I had plugged the numbers in here, and we moved them around. But if you move the formula around first, then you don't have to rearrange the numbers once you have them. So let's go ahead and look at this and see how we can rearrange this. Let's multiply, because we're asking the question of what was the score instead of what was the z-score, what was the raw score. So we want to move everything over to the other side besides that one score and solve for it. So let's multiply by standard deviation on both sides, and we cancel it out on this side. Let's add the mean on this side. If you take the negative mean, positive mean, add it, you cancel it out, but we have to do it on the other side. And so you end up with this formula down here, x equals z times the standard deviation plus m. So essentially, this is your formula that you are going to use to calculate a raw score from the z-score. When someone gives you a z-score and you know the mean and standard deviation of that test, then you can then convert it to a raw score. So you can go both ways, from a raw score to a z-score or a z-score to a raw score. So let's practice a bit. All right, so here are the 3 scores, Mary, Elizabeth, and Joe. And I gave you their z-scores this time. So you have their z-scores. You also have the mean and standard deviation of the tests. I want you to use the formula that we just looked at and calculate their raw scores. So go from their z-scores to their raw scores. Go ahead and pause this video and work out the problems, and then come back and see if your answers are correct. All right, so hopefully these were the raw scores that you calculated. Do you recognize these? These were the scores that you started off with when we started with raw scores and converted them to z-scores. So you can go back and forth, raw score to z-score, z-score to raw score. You'll need to become familiar with this, get a lot of practice so that you understand what they are. These are their raw scores. The z-scores were how many standard deviations away from the mean that their raw score was. Okay. All right. Now, z-scores, if you were to take a whole set of raw scores and you convert them all to standard z-scores, so you take each one, you take each score, subtract the mean, and divide by the standard deviation. You do that to the next score, you end up with a set of z-scores instead of raw scores. If you were to plot these z-scores, so you end up with a distribution of these z-scores on a histogram. You guys remember the histogram, this bottom represents some variable, so we could say this is emotional intelligence, and this y-axis represents the count or frequency of this variable. And so if you were to plot z-scores, the mean of these z-scores, no matter what scores you're dealing with, the mean is always going to be 0 of the z-scores, and the standard deviation is always going to be 1. Now, with our intelligence tests, we didn't start off with a mean of 0 and a standard deviation of 1, but let me explain why the distribution of z-scores always take on this function, these values where the mean ends up being 0 and the standard deviation 1. If we have a distribution of intelligence where the mean is 100 and the standard deviation, so the mean equals 100, standard deviation equals 16. Here's 1, 2, 3 standard deviations up. This next score for one standard deviation away from the mean is 1/16. So if you were to take this score and you turn it into a z-score, you would take the score minus the mean. This score is 100. If you take a 100 minus the mean's a 100, you end up with 0. 0 divided by 16 equals 0. So your new z-score for this middle score is 0, and that ends up being your mean. Your mean gets converted to 0. It gets shifted. Now, if you take this score, 1/16, and you convert it to a z-score, this 1/16 is plus 1 standard deviation above the mean. Now, take that score and convert it to a z-score. 1/16 minus 100 is 16. 16 divided by 16 is 1. So you've now converted this to a 1. And now we're 1/16. That score has now fallen right here and been converted to 1. So once you convert all these scores, the distribution of any z-score is going to look like this. It's going to have a mean of 0 and a standard deviation of 1. And you just remember that that standard deviation of 1 represents whatever the standard deviation originally was. If the standard deviation was 16, the distribution is going to shrink and it's going to become 1. If you had a really narrow standard deviation in your distribution, say your standard deviation was 0.5, then it will widen and it ends up being a standard deviation of 1. So this is what we call a standard normal curve. It's a standard normal curve because it's the same no matter what distribution you start off with. Once it's converted to standard scores, it becomes a standard distribution. All right, so let's take a look at the normal curve. The standard curve is just one type of normal curve. So I'm going to introduce you to what a normal curve is. A normal curve is this bell-shaped curve. You may have heard bell-shaped curve, normal curve. We talked about it a little bit in our first lecture, so you should be familiar with this, but there are some properties that the normal curve takes on. First, the normal curve is bell-shaped. Next, it's symmetrical. One side looks just like the other. If you were to fold it in half, it would be identical on both sides. It's symmetrical. And it's unimodal. Now, you could have a curve that's unimodal, but not a bell curve or a normal curve. It's unimodal, one mode in the middle, symmetrical on both sides. It also has the property that most of the data is directly in the center. So if you recall, this is some variable. We could call this EQ or IQ. And this is the frequency of that variable. And most of the data is in the middle. And as you get more extreme, either higher in emotional intelligence or lower in emotional intelligence, this tapers off. So you get fewer and fewer counts on here. Those are the properties of the normal curve. It's also important to note that these tails extend indefinitely in both directions and they never touch the bottom. Okay? They never touch the bottom of this graph. That means that there are infinite possibilities under this curve. Now, the normal curve occurs in many variables in life. In nature, you see the normal curve over and over and over and over. In fact, that's probably why it's called the normal curve, because this is normal, or it's typical, it's the norm. Most variables, if you think about a variable such as intelligence, most people are around the same average intelligence. But as you get really high scores on the IQ tests, you get fewer and fewer people. And as you get really low scores on the IQ test, you also get fewer and fewer people, so fewer counts. Most things in nature happen that way. There tends to be an average, people fall around the middle here, and then as you get more extreme in either direction, it tapers off. You have fewer and fewer people. Think about height. It's the same thing. There's an average height. As you get taller and taller and taller, so average height might be 5'6". As you get taller and taller and taller, 6 foot, 7 foot, you get fewer and fewer people. Okay. As you get smaller, down to midget size, fewer and fewer people. But most people are around that average. Many variables are like this. Okay. You might think that you go to Starbucks and you get coffee and you all have the same amount of coffee in your cup, but it's not true. There's an average. Okay? They typically fill it, 8 ounces, but it's not exactly 8 ounces. On average, it's about 8 ounces, but every once in a while they put a little less, a little more, depending on how, who's pouring it. So it's going to vary from cup to cup, but most cups will have around this middle range of coffee or caffeine in it, and a few cups will have more, and a few cups will have a little bit less until you hit this poor person over here, that once a year got their cup half full and ended up, driving off and not complaining. So that's how the normal curve works. Now, there are some special properties to the normal curve. Some of the special properties of the normal curve is because the tails extend indefinitely in both directions. It includes 100% of all observances. So I might say, what percent of people score an IQ, in this range or in this range? But if I say what percent of people's IQ would fall under this normal curve, 100%, because these tails extend indefinitely in both directions, it's going to incorporate every single score under this curve. There are some other properties of the normal curve that are very important to remember. Within 1 standard deviation of the mean, so if you go up 1 standard deviation from the mean, you include 34% of observations. So it doesn't matter what the standard deviation is, but if a distribution has this normal shape or normal distribution where most people fall in the middle and fewer fall on the ends, then you will get 34% of observations within 1 standard deviation and 34% below 1 standard deviation. So here we have 68% of data falls in this middle section, below or above within 1 standard deviation, plus or minus 1 standard deviation of the mean. If you go out 1 more standard deviation to the 2nd standard deviation, you add 14% of data. Okay, same thing with below. And so if you add these up, you know that 96% of observations fall within plus or minus 2 standard deviations of the mean. And then if you continue out, you only add on 2% in these tails beyond 2 standard deviations. So that means very few people are going to fall in these extremely high scores, or very few observances will fall in these very low scores. This is important to keep in mind because if we know someone's score, if we know that I scored 116 on an IQ test, that the mean is 100, the standard deviation is 16, that means my score was right here. 1 standard deviation above the mean. The 16 was the 1 standard deviation above the mean. We can calculate the percent of people who score below me and the probability someone would score above me. So if I asked what percentage of people score above me, you just add these up. About 16% of people will score above me, not very many. Okay? Now, if you want to know who scores below me, all you have to do is 100 minus 16, because under the curve you have 100%. So if we know 16 is above, the remainder is below. So you should keep this in mind. Next lecture, part 2 of lecture 3, we are going to talk about z-scores and how we combine what we know about the normal curve and apply that to z-scores. If you know the z-score, you can calculate different probabilities. This is very, very important to understand when we move on to other statistical tests. So if you didn't quite grasp this, I suggest you go back, rewind the lecture, watch it again. Hopefully it'll sink in. It will, believe me. All right, I will see you next time.